All right, so today we're going to do some more tricks for solving integrals that use trig substitution. Today and tomorrow are going to be very similar processes, but today we're going to focus on finding antiderivatives for integrals which have the expression square root of a squared minus x squared in them. And so our whole theme of this unit is to do an integral, sometimes you need to change what something looks like, but not necessarily what it is. So we're doing all different methods of doing that. So right now, when you see root a squared minus x squared in an integral, we are going to use this identity, but we're really going to use x equals a sine theta. So it's sort of like a w substitution, but not entirely. And the reason why we're going to do this will become apparent hopefully in a while. We're trying to, again, make something simpler to integrate. Really quickly, what will this look like? We'll have things like 9 minus x squared. Then I would make x equal to 3 sine theta. Or if I had 16 minus x squared, then I would want to make x equal 4 sine theta, assuming it's the root. And you can even do it if it's square root of something like 7 minus x squared. Your x would become square root of 7 sine theta. So I want whatever is here to be something squared, and of course that would be the square root. So our idea is, though, in general, when I'm doing this, is I want to make x equal to a sine theta. So if I imagine I did that, this identity, or this root over here, becomes a squared minus, I'm going to replace x with a sine of theta. So that will likewise be squared. Now I can clean this up a little bit. I can take, this is the square root of a squared minus a squared sine squared theta. And I'm also allowed to factor out my a squared, 1 minus sine squared theta. And this is where we're going to use this piece right here. This piece right here allows me to say that cosine squared theta is 1 minus sine squared theta. And so I can replace the 1 minus sine squared theta in my under my square root with cosine squared theta. And the square root will undo both of those squares. Square root of a squared turns out to be a, and square root of cosine squared theta becomes cosine of theta. So sort of to summarize, anytime we see this square root of a squared minus x squared in our integral, we can try using x equal to a sine theta. And if we do that, then this square root will become a cosine of theta. So what does this look like in practice? All right, so here's my integral. And I'm looking at this, and of course I'm thinking first, is it a basic antiderivative? Nope. Is it w substitution? Well, I see an inside function, my 25 minus x squared right here, but the derivative of that is not somewhere else in the problem. Possibly integration by parts, I don't know. It doesn't fit any of the things we've been doing with partial fractions or dividing rational functions. So I see this root, and you should say in your head, oh, there it is. There's my a squared minus x squared, right? A squared minus x squared, the root of that. That's what I see right there. And if that's true, then a is 5. And so when I see that, I'm going to say I want to make x equal to a sine of theta, right? So now, what we have said in what we just did is that I can replace then this. If x is 5 sine theta, then root 25 minus x squared we know is going to equal 5 cosine theta. If you forget about that, if you get about what the result is, you can of course do, well then root 25 minus x squared will be root 25 minus 5 sine theta squared, which becomes 25 minus 25 sine squared theta, still under my radical. And hopefully you can continue the process and say I have my 25, 1 minus sine squared theta. Oh, that's cosine squared theta, and the square root of cosine squared theta, or square root of 25 is 5, square root of cosine squared theta. So hopefully you can remember all that. If not, you can always do that process. But now I still have other things to fill in. I know what x is, so I can fill in my x. That's awesome. I still have one more thing to replace, and that's my dx. You can't ignore your dx. People like to do that. They like to think, oh, that's not really important. But particularly in a substitution, your dx is extremely important, and you will not be successful in finding an antiderivative unless you account for the fact that you need to replace dx with something about theta. That's our job. We're trying to replace all the x's with something about theta. So in this case, if x is 5 sine theta, dx will be 5 cosine theta d theta. Don't forget about your d theta, your dx, your d whatever. They are important. So now I can try my substituting. Dx is going to get replaced with 5 cosine theta d theta. X is going to get replaced with 5 sine theta. So I'm going to square that x. And my root 25 minus x squared is going to be replaced with 5 cosine theta. So now everything has been that involves x has been turned into something about theta. Now when I look at this, I can say, that 5 cosine theta on top will cancel that 5 cosine theta on bottom. I'm going to square both my 5 and my sine theta, and I'm going to have d theta over 25 sine squared theta. I'm still integrating. And I always like to pull out my fraction. And sometimes I think when I'm trying to see what something is, it does help to sort of separate out the d theta. Now, sine squared of theta. I start thinking about w substitution because I have a function inside another. However, that won't work. It doesn't really do our m and n with evens and odds. So what else does 1 over sine squared theta equal? And if you are quick and you've been studying those last 3 integrals, you would recognize that 1 over sine squared theta is the same as cosecant squared theta d theta. And hopefully now you say, oh yeah, that looks familiar. That is the derivative of some function. Cosecant squared theta is the derivative of negative cotangent of theta. So we are now at a point, we have done our thing and we have made it look like something we know. So I have 1 over 25 cotangent of theta plus c. Awesome. And you're thinking, now we're done, except for one little problem. If we look back at where we started, everything was about x. Now everything is about theta. So I have to go back to x. And how am I going to do that? Well, to do that, I'm going to remember what I started with, which was that x equals 5 sine theta. And so I don't really want to know what theta is and replace it. While that is possible, mathematically sort of cleaner and more elegant to just, I want to replace cotangent of theta with something. And I'm going to use this equation right here, and I'm going to solve for sine of theta. If x is 5 sine theta, then x over 5 is sine theta, and that gives me this picture right here, which says that if I have some angle, theta, in a right triangle, sine of theta is x over 5, then my opposite side over my hypotenuse must be x over 5. And then if I used Pythagorean theorem, a squared plus b squared equals c squared, I would know that if I have the hypotenuse and I square it and I subtract the other leg squared, I would get, and I take the square root of that, that would give me that missing leg. And so this is now my picture for theta. And I could tell you what an expression for cosine of theta, sine of theta, tangent of theta, cotangent of theta. And when I come to replace up here now, my 1 over 25 stays here. Cotangent of theta, I'm going to replace with the ratio, with the cosine of theta over sine of theta, or the adjacent over the hypotenuse. So if my theta angle is right here, my adjacent side is root 25 minus x squared. My hypotenuse is 5. There is a replacement for cotangent of theta, and I can add my plus c. All right, so now if I think back to this picture, because that is what I started with, was that root 25 minus x squared. And if I think back over here, Anytime I have x equals a sine of theta, I will always have x over a equal to sine of theta, and I will always have this picture where theta is here, x is my opposite side, a is my hypotenuse, and my adjacent side will always be a squared minus x squared. So if in my antiderivative I have any function that involves the adjacent side, I will have root a squared minus x squared. And I can use this triangle basically similarly to the fact that when I use x equals a sine theta, the square root becomes a cosine of theta. This is always the triangle that I will use to find my to find my way back to x. All right, let's try another one. So again, I'm looking at this. One is not the derivative of the other. W substitution doesn't seem like a good option, but I see my square root of a squared minus x squared, and so I'm going to make x equal to a, which in this case is 3 sine of theta. Dx then will be 3 cosine theta d theta. And I know that 9 minus x squared is going to become, it's not the same as, but it's going, yeah, it's going to become 3 cosine theta as well, based on my substitution. You can do the substitution, but hopefully the more you do it, the more you'll remember how to do it. So we're going to do our substituting now. X is 3 sine of theta. I'm going to cube that, and then I'm going to replace the root with 3 cosine of theta, and then I have to replace dx with another 3 cosine theta d theta. Let's move that all down just a little bit, so I have a little more space. Let's try and clean this up a bit before we proceed. So I'm going to cube my 3. That gives me 27. I'm going to have sine cubed theta, and I'm going to have 9 cosine squared theta d theta. And I can even pull out my entire constant, which is 243. And then if I look at what's left, sine cubed theta, cosine squared theta, d theta, I think, okay, now what? Well, again, you have all these tricks and these tools in your toolbox now. You go back to, hopefully, you can get there. What is this like that we've already done? And what it's like is I have sine theta to a power, cosine theta to a power, where the sum of the powers is odd. And when that's true, I'm going to make my w equal to the thing that's to the even power. So w is going to be cosine theta, and dw will be negative sine of theta d theta. And how we make this work is I'm going to keep my 243. I'm going to steal one of my sines. So I have sine squared theta, cosine squared theta, d theta. Oh, and then I'm going to steal one of the sines and I'm going to put it out here. Sine of theta d theta. And I'm trying to replace everything with something about w. If I think about all of this, right, I know that this part right here is related to the dw. It's the same as that. So negative dw is sine theta d theta. So I have that covered. I can replace my cosine squared theta. This is going to be covered by my w. But then I need to deal with the sine squared theta. So I need to write sine squared theta in terms of cosine of theta. And again, my helpful identities, sine squared theta is the same as 1 minus cosine squared theta. I have a cosine squared theta, and I have a sine theta d theta. Now I can work my magic replacements using w's. So I'm turning all my thetas into w's. So I have 243. 1 minus w squared times w squared times negative, I'm going to throw my negative out here, dw. And now I need to do this integral. This is sort of the problem that keeps giving. My negative 243, I'm going to integrate, I'm going to distribute. So I'm going to get w squared minus w to the 4th dw. Ha, at last, something I can find an antiderivative for fairly simply. Negative 243. Antiderivative of w squared, 1/3 w cubed. Antiderivative of w to the 4th, 1/5 w to the 5th. We have a plus c. Now, I have to go back to x. But I don't know how to go back to x yet. What I do know is that w is, again, cosine of theta. So I can replace all my w's with cosines of theta. Negative 243, 1/3 cosine cubed of theta. Oops, I'm going to theta. Minus 1/5 cosine to the 5th of theta. So now I'm one step closer, and I have to go all the way. I have to go all the way back to x. And so I need my very original substitution, which was x is 3 sine theta. So x over 3 is sine theta, and if you think about your picture, here's theta, opposite is x, hypotenuse is 3, adjacent side must be 3 squared minus x squared. And so I get my final answer, negative 243, 1/3 cosine of theta is root 9 minus x squared all over 3, because it's adjacent over hypotenuse, cubed. And I'm going to do minus 1/5. I need to come down a little bit. 1/5. I have cosine, which is, again, is root 9 minus x squared over 3 to the 5th. And I have my final plus c. Hopefully, now you can tackle your homework.